Start week 4, three-phase systems. We're going to look at this week is first of all go through and sort of justify why we use a three-phase system. I've got some copies of these board notes for you. I'll give them out in a minute. Secondly, look at the relationship between, so once we know what a three-phase system is, and so on, relationship between line and phase voltages and currents, line and phase currents for balanced star and delta connected systems. Then we'll have a look at the power in balanced star and delta connected systems and some solving of some three-phase system problems. All balanced this week, apart from one question in the tutorial questions is about what happens when one phase gets disconnected. That's not a particularly difficult one. Okay. Right, so let's have a look then. If we start off looking at what we'd have from a three-phase system, a single-phase system. If we wind a coil in a stator and have a permanent magnet between it, we can have a position like that, one on the left, where the coil is in the field and we would induce a voltage, and in this position the coil's not in the field and therefore we wouldn't induce any voltage. So when I saw that position, the generated EMF between the terminals A and 1, i.e. across the coil, is equal to B times L times V, and that's where B is the flux density of the field, how much field we've crammed into the permanent magnet effectively, how dense it is. L is the length of conductor that is inside or experiencing the change in that field, and V is the velocity at which it's cutting across, the field is cutting across the conductors. So without any movement we don't get any voltage induced, and we can vary the amount of voltage induced by changing the field strength, putting more conductor in the field, or turning the damn thing faster. Okay, so that's the type of voltage output waveform we would get from one single coil. It's at peak when north and south are top and bottom as in the diagram, and it's at zero when the coil's completely out of the field, and then all other points in between creates a sine wave or a cosine wave, that one is. So if we then look at the power in that single phase system, so if we connect a resistance or a load that's going to dissipate some watts to that coil, well, then a current will flow because we got a closed circuit. And if that's a pure resistance so that we don't have any phase difference, and that's what we're going to consider at the moment, just connecting fairly resistive loads, we would have an instantaneous current. For instance, we got a voltage here peaking at 20 volts, and our instantaneous current here is starting at peaking at 10 amps. But the two waveforms follow each other. If we then say that the power at any instant in time is equal to the instantaneous current times the instantaneous voltage, which it would be for a purely resistive load, we can then plot the power for that particular generating system over time as well. What we end up with is a pulsating waveform that's always positive above zero. Okay, the frequency of the pulses is twice that of the frequency of the sine wave creating it. So what it's effectively done is taken the bottom half and put it on the top, and we're getting peaks of around 200 watts here. Right? What that does is present a pulsating load to the prime mover that's rotating it. Your steam turbine, diesel generator, mice in a wheel, whatever it is that's turning it, are experiencing a pulsating load, which will set up mechanical vibrations, making it, and tend to make the generator noisy, cause wear and that type of thing. So you wouldn't particularly want an extremely large generator of that design. It's okay for small scale stuff. So if we then consider what happens if we add a second coil, coil B-2, positioned 90 degrees around from coil A-1, it produces an identical sine wave 90 degrees out of phase with the other one. So the blue one there is the voltage from coil A, the red one the voltage from coil B, 90 degrees out of phase with each other. If we do the power, if we plot the power for that, so we connect a similar load, RA and RB, to each of those windings, what we get is a power curve for winding A and a power curve for winding B. If we take the total power at any instant in time, i.e. add those two together, we get a straight line at 200 watts. Effectively, the power from B fills in the gaps in power from A, and therefore we get a straight line power, but at 200 watts. So the extra power is produced without any discernible increase in the size of the generator. All I've done is added an extra coil 90 degrees out of phase with the other coil. Okay? So that's what happens if we was to go for a two-phase generator. So why go for a three-phase one? If we add a third coil, winding C, that is C-3, we'll end up with three coils 180 degrees apart from 120 degrees apart from each other. So here's the start of winding A, the start of winding B is 120 degrees round, the start of winding C is another 120 degrees round from that. We then get three sine waves, all 120 degrees out of phase with each other. What we get when we plot the power are three power curves, each pulsing twice for every time, for every cycle of their respective voltage sine waves. When we add all of those together, we get 1.5 times the power we got with the two-phase generator, but again with no discernible increase in the size of the actual generator. And also both the two-phase and the three-phase generator provide an even load to the prime mover, and therefore we don't get the vibration and the mechanical wear that goes with it that we would get from the single-phase generator. Okay, so no discernible increase in size of the generator, less vibrations, more power from the same size. That's three considerable reasons for using three-phase without the system requirements that means we can have dual voltage system and all of that type of stuff that we're coming on to a bit later on. Okay? So, moving on then to balanced three-phase circuits. Three-phase power system will have a star, or the Americans call it a Y-connected generator, the three phases. And that's the resemblance of either a star, or if you turn that round for 180 degrees, it looks like a Y. All the phases are displaced by 120 degrees. It's a balanced source. Okay. The generator can have loads connected in either star or delta formation. Okay, so down the bottom there, star formation, delta formation. That one's named after the Greek letter delta because it looks like it. Okay, generators are rarely connected, if ever, or rarely connected in delta. The reason is, unless you have a perfectly balanced load, what you'll get is an overall voltage around there. They won't cancel each other out, and it'll cause circulating currents in the three windings. That all it does is serve to heat the windings up. Okay, so generators connected in star. So what you'll end up with is a system that's got a star connected generator with a star connected load, or a star connected generator with a delta connected load. Yeah. Furthermore, if you was to connect in delta, your phase voltages would be higher, and therefore you'd need more insulation in the windings. Okay, so there's a number of reasons why you don't connect in delta, but the main one is this circulating current issue. Because if you can find very many perfectly balanced loads, you'd be a lucky person, because even your average motor is not a perfectly balanced load. Alright, but connecting it in star, generating in star gets around that problem to a certain extent. So, relationship between phase and line voltage for a star connected system. This is your average star connected system, and I've included the neutral from the star point. Okay. We have three phase voltages, EA, EB and EC. So we've got three lots of phase voltage between the lines and the neutral. So we've got a phase voltage there, one there, and one there. They're your phase to neutral voltages. If we say, by Kirchhoff's law, the line voltage, and we'll pick this one between EA and EB, the line voltage there by Kirchhoff's law, EL, is EA minus EB, and it's negative because that arrow's going the opposite way. Yeah? Okay? So we're looking at that, by Kirchhoff's law, EL is EA minus EB. So from that, we can draw a phasor diagram. Here's EA up here, this one. EB is 120 degrees out of phase down that way. So minus EB is this dashed line up here. And then we add the positive EA to the minus EB using a parallelogram, and we end up with a line voltage that's 30 degrees out of phase with one of the phase voltages. And if we was to draw all the line voltages on there, each line voltage would be 120 degrees out of phase with each other. But that diagram gets rather complex, so I didn't bother to do that. Alright, what we do to one, if we done it to all the others, it would be effectively the same. Using that triangle there, this one, because there's 120 degrees in there, and there's 30 degrees in there, we can use the sine rule for non-right angle triangles to say that EL, the length of the line voltage phasor, over sine 120, the opposite angle, is equal to E phase over the sine of the 30 degree angle. Rearranging that equation, EL is EP times sine 120 over 130. That equates to the square root of 3, if you do that on your calculator, and therefore the line voltage for a three-phase star connected system as √3 times the phase voltage. And that analysis would be the same regardless of which phase voltage and line voltage we picked. Okay? So in summary, for a star connected system, E line is equal to √3 times E phase. Over the page, relationship between phase and line current for a star connected system. Well, if we look at that diagram, we've got a line current travelling in the top line there, line A. That must also be the current travelling in that phase. There's nowhere else for it to go. So for a star connected system, the line current and phase currents are equal to each other. Okay, so IA, IB and IC are all equal in magnitude, and that's quite an important statement, that magnitude, because they aren't equal in phase, remember. Okay. If we go on to the next page, we'll look at the fact that that can show that in a balanced load, so if everything is equal, all the line voltages are equal, the three impedances are equal, we've got a perfectly balanced load, IA and IB and IC are equal in magnitude, and the phase angles are exactly 120 degrees, we can prove that the instantaneous current flowing in the neutral is 0. And we're using the complex number system we've been working with the last 2 weeks. We can prove that. If we let the peak current be an amp, and phase A is the reference phase, the one without an angle, 0 degrees, we can say that the current in A is 1 angle 0, or 1 plus 0J amps. IB at the same time would be 1 angle minus 120. That's minus 0.5 minus 0.866 J, and the third one is 1 angle minus 240 degrees, and that is, we could equally put plus 120 there and that would mean the same thing, minus 5.5 plus 0.866. And it don't take a calculator to say that if you sum these up, we end up with 0 minus 0 J ohms, amps, sorry, and therefore we have no current. Okay? But if we unbalance any one of those loads so that the current in one of them changes, we then have a current flowing in the neutral. So that's why it's important to say the magnitude of those currents is equal, because if we're saying an amp is flowing down here, an amp down there and an amp down there, saying 3 amps going into that junction and 0 coming out of it, it doesn't make sense. But at any instant there will be, because of the phase angle differences that cancel each other out. Again, any questions about that part? I have a blank slide. Right, relationship between phase and line currents for a delta connected system. Here we've got our line voltage delivering voltage to the system, 3 of them, one between IB and IA, one between IB and IC, and one between A and C. We get 3 currents, I1, I2 and I3. They're the phase currents flowing in the individual loads. If we look at the top junction here, we can write that IA is equal to I1 minus I3. and that we know that the current I1 is going to be in phase with the line voltage. Must be. This voltage is putting current through there, and therefore they must be in phase with each other. We can draw the phasor diagram again of that situation. So I've got EL up here showing that current I1 is in phase with it there. Here's I3 down here, and there's minus I3, this dotted line in here. So we've gone plus I1, minus I3. This phasor in here is our line current. It's 30 degrees out of phase with the phase current. That's the addition of the two. We do the same maths as before, using the sine rule on that triangle. IL over 120 degree sine 120 is equal to I1 over sine 30. Rearrange all of that, and we end up with the line current being √3 times the phase current. Yeah? And in a delta system, the line and phase voltages are equal to each other. So the currents are equal in star, the voltages are equal in delta. Yeah. What you have to be careful with, a bit later on when we do a delta system connected to a star generator, your line voltage at your load is your phase voltage at the generator. And you'll see that when we look at the connected system. Okay? So you have to be a bit careful there. So, quick summary of the star-delta situation. In a star-connected system, line voltage is √3 times the phase voltage. Line current is equal to phase current. We've got three line voltages 120 degrees out of phase with each other, and three phase voltages 120 degrees out of phase with each other, and 30 degrees out of phase with the respective line voltages. In delta, line current is √3 times the phase current, line voltage equal to phase voltage, three phase currents are 120 degrees out of each other, phase with each other, three line currents 120 degrees out of phase with each other, and they're 30 degrees out of phase with the respective phase currents, that should be voltages. I think I should have put currents there. That's what copy and paste does for you. You must make sure you edit all the voltages to currents. Everyone okay with that? So that's a summary of what everything we've been through with regard to the differences between the two systems. So, power for a three-phase system. If we draw a circuit of a three-phase system, as shown on the diagram there, the line currents and phase currents are equal, and the phase voltages are EL over √3. Yep. So, for each of these loads, if we take a load in isolation, we can say that the apparent power is the phase voltage, which is EL over √3, multiplied by the line current, because that's the line current that's flowing through each one. Okay, so for a balanced system, the total power must be 3 times that. Yeah, 3 times EL over √3 times IL, and 3 over √3 is equal to √3. Therefore, the total power is √3 times EL times IL for a three-phase star-connected system. Furthermore, Since the phase voltage is given by EL over root 3, we can also say the apparent power for a star connected system is 3 times the phase voltage times the line current. Okay, so it all depends on what you've been given as to which one, whether you use that or that. Yeah. So that's the star connected system and power. Okay. If you're, for obvious reasons, if your load is not balanced, then you've got to calculate each load individually and then add them together. But for a balanced system, we could look at one in isolation and multiply it by 3. So, power for 3-phase balanced load, delta. In this circuit, we've got current voltage across each load is the same, EL, the line voltage, EL and E phase are equal, but the phase currents are IL over root 3. So for this system, the apparent power for each load is IL over root 3 times EL, and again that follows through. To get the total power, we multiply that by 3, and that cancels out to root 3 times EL IL. Please be warned, just because those two formulas are the same doesn't mean the power is the same in a star or a delta connected load for the same given impedance values, because it won't be, because that's going to change them. Taking the same load, same motor, and connecting that up in delta instead of star means that the currents will be different, so there will be a difference. Okay. Furthermore, since the phase current is given by IL over root 3, we can write that the total apparent power for the delta connected system is 3 times EL I phase. Yeah? Okay? Just before we go any further, and I didn't put it in the notes because I thought of it after I'd got them printed. What the notes was, all values so far are the RMS values of the voltages and currents. Yeah, we're not talking about the peak values here, we're talking about RMS, or the effective value. Can anyone remember what that means? The equivalent DC value of an AC waveform, yes. That's the value that would give the same power as the same voltage in DC. Okay. If you want the peak, that's equal to root 2 times the RMS value of a waveform. And there's a question in the tutorial sheet this week that will require you to know that. Okay? So what we'll do now is we'll have a look at 2 or 3 problems, and then we'll take our customary break, I would expect. So, first of all, a 3-phase motor connected to a 440 volt line draws a current of 5 amps. The power factor of the motor is 0.8. Calculate A, the total apparent power, B, the total active power, and C, the reactive power absorbed by the machine. How are we going to do that? What's the plan of action? So this is S in VA. What about the active power? P in watts. Reactive power? Q in var. So we're probably going to end up looking at something like this. P, Q, and S, and we got a cosine of that angle is 0.8. Yeah. So what can we do to find the first value with regard to that triangle? Give me the formula, Joe. Does it involve doing anything with the line phase? Do we? It's connected in. It's connected in star, right? S is root 3, E line, I line. Yeah, and if it's connected in delta, S is root 3, E line, I line. Yeah? So no, we don't in this case need it to be specified that's connected in star or delta. So S is root 3 times EL times IL. That's root 3 times 440 times 5. Yeah. 3,000 810 VA. 3810 VA. What can we find now? What's the formula then? Cos of the angle is P over S, which means P is S cos the angle. So that is 3810 times 0.8 equals. Okay? 3048. No, that's not what I'm looking for. Onions, tomatoes, watts. Yep. And then the last bit, C, Q is equal to square root of S squared minus P squared times root 310 squared minus 3048 squared equals 2286 var. Yep. So that's reasonably simple, isn't it? Really? If you know and remember the formulae. Yes, you will have a sheet in the exam, but it won't be every rearrangement, and you'll need to know how to use it and when to use it. So what about this problem then? A balanced three-phase load may be considered sorry, this is solving three-phase balanced load problems. Balanced three-phase load may be considered to be composed of three identical single-phase systems. Ah, you know that blank slide I had earlier? This is meant to be where that is, I think. Right, three identical resistors connected in star across a three-phase 550 volt line, dissipating a total active power of 3000 watts. Calculate the current in each line, the value of each resistance, the total power dissipated if the same load is connected in delta. How are we going to tackle that problem? You've been given the line voltage 550. Yep. What's the wattage of the total power of 3000? So what's the power of each of them? So P is 3000 over 3 is equal to 1000 watts. So we might be able to do something with that. Yeah. We can only go watts here because they are resistors. If they was down as an impedance, we've got to be careful. We'd have to be talking about S. Yeah. It's the power for each phase of the load. Yeah, it's balanced. It's a phase power. Yeah. What can we get now? What do we need to get something else out of that? What else could we calculate from what we're being given? We want the line current because that's what the line current for a star system, Keith, is the same as the phase current, isn't it? So how can we get the phase current out of that? We've got a formula P here, that PR, we could also say is IL times E phase. Yeah, the phase voltage. What's the phase voltage? How can I calculate the phase voltage here? Yes, so therefore it's equal to IL times EL over root 3. Yep, because that is equal to that. These two are equal to each other. Yeah? And it's probably best to do it that way rather than calculate it separately and rounding it. So our line current is not as sorry, this is oh yeah, we've got to rearrange, haven't we? Because we want the line current. So IL is equal to power in each phase over EL over root 3. That's 1000 over, what was my line voltage? 500 something. 550 over root 3. Someone can push the button. 3.15. I've got to say it once, even though we're in here. Amperage. Yep. So our line current in a star connected system is 3.15 amps. So from that, can we find the value of each resistance? R is equal to EP over I L. That's 550 over root 3 over the 3.15 amps. And again, someone will put what we got. .8 ohms. Okay, so what we now got to do is work out what would happen power-wise. I think it is. What's the last part of the question? To get all power dissipated if the same load is connected in delta. How do we calculate the new power? We'll go with 100. We'll not worry about the 0.8 of an ohm. So how can I calculate? Now we've got different currents here, haven't we? This is IL. We've got 3 I phases. But line voltage and line and phase voltage now are equal. So what can I calculate? All I got at the moment is 550 volts and 100 ohms. Which current, Joe? Sure. IP, can't we? We've got 550 volts. If we isolate that one load, 550 volts across it, yeah? Agreed? So that's E line over R. That's 550 over 100 5.5 amps. Yep. How does that compare with the previous current? We know that S is, in this case, equal to P, which is equal to and IL is equal to that. Therefore, S, or total power, is equal to root 3 times EL times root 3 times IP. All of that. Agreed? And those two cancel out, don't they? They become 3. Root 3 times root 3 is 3. Isn't it? I don't know if that quite sound enough to me. With 9,075 watts. You spotted my deliberate mistake, Keith. Yep. For that circuit, calculate the current in each line and the voltage across the inductor terminals. How are we going to do that one then? It's 3 impedances now. How can we turn one of these? So we don't actually, for this problem, we don't need to get involved with J at all. How can we calculate the magnitude of Z? Because all we're interested in is the magnitude of the current, not its phase angle. You're not being asked for its phase angle. Yeah? So if we can just deal with the magnitudes here. So how can I calculate the magnitude of Z? That would be Z1, Z2 and Z3, but we can deal with one of them and then get the total power or the total apparent power from there. Think of that diagram. R, XL, Z. And you've been given this, you've been given the inductors as not as Henrys, but you're given an ohmic value for them. So you've been given XL for those. So by Pythagoras, you're right, Joe, Z is root 3 squared plus 4 squared. What do we get? What for current? 50.8 amps. I'll go with that. So we got a phase current of 50.8 amps. That will be the current in a line as well. Okay, so B, we'll find S. S is equal to We can get the total power in one go, hopefully. They're the same. You look. Still big. What is it now? Sorry? 38,000. kVA. It's a hefty old load. So we'll do that. VL, how can I get that? I line the what, Joe? Which is the XL, isn't it? Yeah. So it's the 50.8 times the 4 ohms is 200 and something. Volts. Last but not least, 3-phase 60 Hz line connected to 3 identical capacitors in delta, as shown. If the line current is 22 amps, calculate the capacitance of each capacitor. How do we do that? What do we know? What? How can we get C out? What can we get C out of normally with this type of problem? Yeah, that thing. So we know that XC is 1/2 pi FC. That's why you've been given the frequency in this problem. Yeah. So if we can find, that means we know F. We want to find C. So if we can find LC somehow, we can do that. So we need to find a way to find the capacitive reactance here, or the impedance of these capacitors. So we got 22 amp line current flowing. Okay. We've got a phase voltage, so across each capacitor, because these are in delta, these capacitors, we've got 550 volts. Line and phase voltage are the same. We know this current, 22 amps. If we can find the phase current, we can use that and the voltage to find XC, can't we, using Ohm's law? These problems are really not much more than basic electrical calculations. They just seem more difficult. So what do we need to, what is IC equal to from what we know? The current flowing in each capacitor? Joe, i.e. the phase current. How can we calculate the phase current here? IL over root 3 is 22 over root 3 is, what did you say it is? 12.7 amps. Therefore, XC, the impedance, must be equal to EL over IC, that's the 550 over 12.7 equals ohms. Yeah. Notice we're not having to get involved with any kind of angles or complex numbers here, because we ain't interested in the phase difference. So now, because we know that XC is 1 over 2 pi FC, that rearranges to C is 1 over 2 pi FXL. XC, sorry. Which is 1 over 2 pi times 60 times 43.2 equals. Who's pushed the buttons quickly? What? Yep, 10 to the minus 6, is it?